Good morning, everyone, and welcome to the second webinar with isoenergy in a series of 4 over the next couple of Fridays and the one previous. My name is Will McCarthy and I'm a consultant for isoenergy based in our West office in Tewkesbury. And I'm here today to talk to you about best practice in terms of designing the heat collection method, the heat collection element of heat pump systems. So understanding how best to take heat from the environment around you using ground or water source technology, and the various different methods that can be designed to work within the different settings that you might find yourself within. Myself personally, I've been involved in renewables now for 11 years or so across all forms of renewable energy, and today we're focusing particularly on heat pumps and the expert and the specialist design features behind them. So some of you may have joined our podcast last week. If you have, then we've covered some items in there, but not all. We're focusing on a lot of new stuff as well. If you do have any questions or queries, there's a question and answer feature within the server, the portfolio itself. So do feel free just to type in any questions on the Q&A, and my colleague will pick those up and we'll answer those all at the end of the presentation. So without further ado, I'll introduce you to ourselves, isoenergy. We are a team of 60. We're involved in all forms of renewable energy. We've been founded in 2006, and we turn over around £8 million a year with over 1,000 installations to our name. The vast majority of those installations by default have been heat pumps, just simply because that's where we've made our name and that's where our expertise started. But we do cover everything from solar, PV, right the way through to biomass, car charging points and everything else in between. We're based, our head office is in Hawley, and we also have our West office in Tewkesbury, and from there we offer national coverage. We have the ability to consult, design, install and maintain in-house. So everything we do is done within our company walls, and from the very start of the conversation right the way through to the handover, the RHI application and looking after your system long term, we can do that with the employees that we have. The first thing we would do if you're looking at a ground source heat pump system or a water source heat pump system is just simply consult you on the different options that are available to you. It's really difficult to pick through what is the myth, what is myth, what is practical, what is not practical, how things can be done, and the various costs in between. So what we do as part of that consultation is obviously understand clearly what you want to achieve, what you want, and what the building needs. And really how to do that. And then obviously from there, we have the ability to provide you with very accurate costings, benefits, savings, features that we could take advantage of, which will further improve the value of your investment. And obviously working within the difficult confines of perhaps a difficult to heat building or a large new build where there's lots of different trades and contractors on site that need managing carefully. We then design. So that moves, the consultation moves forward to a design approach, and we come back to you with full details on every single bit of equipment we're going to be installing, how we're going to install it, what it's going to look like, where it can all go, and obviously then manage that as part of the implementation of the system, which comes through with the installation. So we have 2 in-house groundwork installation teams. In fact, I think we've now got 3. Number of plumbing teams, a number of electrical teams, and we focus particularly on the best quality fittings and fixtures. So what we won't do is cut corners in terms of materials or pipe size or pump size or size of tanks, and therefore we're doing this deliberately to maximize the efficiency of the system. And we can come on to that in the presentation, but it's really important to understand that from the start, that as a company we hold efficiency and performance of our systems above all else. We do subcontract some of our specialist work, so borehole drilling, for example, and you'll see examples of that in the presentation, but everything else essentially is done by us. And then most importantly, I think it's all very well fitting the systems, but if you can't look after what you fitted, then what's the point? So we do maintain everything we install as well, and we offer full service packages, and those packages range from varying levels of support depending on what you want us to do. But essentially, but the way we design our systems, and I think my colleague Bertie might have alluded to this last week, the way we design our systems allow us to provide a nationwide coverage, so we can provide you with that ability to service and look after your system from the very top of the country to the very bottom. So I think the first thing to think about before we just jump into how we can design these systems is why people consider renewable energy and why it's worth looking at now. The main one really is the running cost reduction. If these systems are designed correctly, you will reduce your running costs quite considerably. And you should expect a significant saving, particularly if you're off the mains gas grid. So you will hear that sometimes you might find online that heat pumps are expensive to run, or they cost me a fortune in electricity. We're going to show you how and why you shouldn't expect that with our systems, in particular in terms of best practice. But really, if these are done right, you should expect a significant reduction in running costs. Ultimately, you should also expect an improvement in comfort levels. And the method at which a heat pump operates, it runs at slightly lower flow temperatures around your central heating system, but it maintains that temperature for much longer periods of time. So essentially, you're warming the building to a point and then just keep topping that heat up rather than heating from cold 2 or 3 times a day. And that, in turn, often leads to an improvement in comfort levels, and it improves, obviously, the feel in the building. The big one and the word on everyone's lips at the moment is obviously carbon, and the electrification of heat is very much happening. So if you are looking at this presentation as part of future proofing, as part of looking at this as an option going forward, then you are in the right area. Heat pumps are going to become much more mainstream. And the reason they're going to become much more mainstream is because the government have committed to a program of decarbonisation, and heat pumps reduce carbon by up to 60% in a building using mains gas, and over 70% for anything using oil or LPG. So it is one of the biggest things you can do in terms of reducing your carbon without changing your lifestyle, I think is the best way to put it. And then again, the other thing to think about is incoming legislation. So if you're thinking about building a house, or if you're thinking about renovating, or you're thinking about extending or buying a property which is perhaps using fossil fuel at the moment, then by putting in a heat pump, you are ahead of the curve. And being ahead of the curve means you do receive incentivized payments. And they are, in some quarters they're finishing, but in some they're very much available, and a part of isoenergy's consultancy service at the start of an inquiry is to obviously navigate you through that and make sure you clearly understand how and why a system should be set up in a particular way to maximize the value of the investment that you're making. So focusing on improving comfort levels, essentially how we do that is to use the thermal mass of the building. So when you often find big listed buildings, for example, big thick stone walls, we're able to use those walls to our advantage by essentially warming the walls and keeping the building at a constant temperature. So part of that would be to complement that, we'll obviously look at reducing drafts and reducing heat loss, but ultimately, as long as we understand exactly what the building needs, then we can design a system to heat any type of property out there. In terms of the contents of the property, a lot of historic estates that we do a lot of work in, and we don't just do big properties, we do everything else, but a lot of these big properties with lots of very valuable pictures and antiques, the contents is essentially conserved a lot better with the method of heating that a heat pump provides, that sort of constant temperature held and maintained throughout the year. In terms of hot water, it's often asked, will I have enough hot water for my bath? I've read online somewhere that I won't get enough hot water. Again, if it's designed correctly, you will have plentiful amounts of hot water, and there'll be nothing too dissimilar from a conventional fossil fuel system. We store water at 55 degrees. That is far too hot to bathe in. A hotel and hospital limits the output of water temperature to around 40 degrees. So it gives you some idea of just how warm the system can get to. In terms of carbon, as the slide shows you, we're looking at heating emissions taking up about 18% of the UK's total carbon footprint. So it is very much front and centre from government policy currently and going forward. You can expect a significant carbon reduction, as we highlighted, and that is why the industry is so heavily incentivised at the moment. But those incentivized payments will be finishing, and the carrot will be replaced by the stick. So that is coming around the corner. To what extent, we're yet to find out, but we're expecting some fairly big announcements in the coming months and years. So in terms of future-proofing the building, like I say, here's some more detail about why you're future proofing, but ultimately fuels like oil and LPG in particular, and then for leading into the mains gas, they are going to be phased out to be replaced by heat pumps. If you imagine the way that the country's the position the country's looking to get to is how you might look to get to if you're building a house. You might be thinking about putting in a heat pump with solar. So you have a solar PV array complementing an electric heat pump system. On paper, that looks like it's a brilliant solution, and if it's designed correctly, it will work very, very well. The exact same principle applies, but on a mass national scale. The government have very much focused in the previous years on generating green electricity, green energy. You often hear about how much electricity that day has been produced by wind or by solar. So really what they've got then is a situation where you've got a huge amount of electricity being produced by green sources, which can then feed into green heating. And therefore, the impact that we have as a country on our carbon footprint is significantly reduced. So the benefit of having a heat pump is that you do future-proof your building against these incoming changes. Carbon taxes, they're likely to come around the corner. They're muted, they're whispered about in corridors, they're talked about in the background. And from an industry perspective, I think as long as they get a grip on fuel poverty, the introduction of carbon taxes is actually not a bad thing to move people onto heat pumps and to move people into renewable technology. I think we should expect that to come around the corner in the coming years. It may not be a popular decision, but it certainly will be a decision that might need to be made sooner rather than later. So moving on to the subject of our presentation today, what we want to focus on is obviously the different ways that we can collect heat using heat pump technology. Obviously, we have air source heat pumps, and we have a presentation on that coming next week. But in terms of ground and water source heat pumps, there's a number of different ways we can do that. So for example, with a ground source system, you can have ground loops in the ground or boreholes. And with water, you can have a closed or an open loop water source system. And we're focused more on closed loop today, and I can explain the reasons why as we go through. Or you can take water from a flowing source. And that's a very interesting technology which we've used and implemented in a number of different buildings across the country. And from there, you will have a clear understanding of exactly how you could design a system to suit the needs of your building or the land around it. So if we start with the horizontal array, I think this would be described as probably the more popular or the most common way of using ground source technology. And essentially what we're doing here is opening up a number of trenches, putting in pipework within those trenches, closing them all back up, putting a bit of seed down if needs be, and letting the system just do its work, or so it seems. It is actually a lot more complicated than that in terms of a design practice, and a good design means that you have to take into account a number of different things. So for example, here what we have is a large collector array feeding a house to the north west, and from there you can see we've got 3 different manifolds. So essentially we've got 3 service points for the collector array in the ground. We've got headering pipework linking those manifolds together, so they're all individually serviced from the same flow and return pipe, which then runs to the plant room. The collector array is sized using the geology of the land around us, so how much heat can we get from the ground, and that depends on the type of geology that might be under your feet. For example, clayey soils are going to give us a bit more heat than sandy or chalky soils. But essentially, in terms of the collector array itself, another key part of that is obviously pipe sizing. So it's really important that when you size a collector array, you're obviously understanding how big the pipework is, how much flow you need through that pipework, and are the pumps within the plant room that are used to move the energy from field to house and back again, are they going to be working too hard? And ultimately, when it comes to the design practice that we implement in our systems, we do a flow calculation on all collector designs, be it borehole, lake, ground or water. And that allows us then to know that we not only have sized our collector array to meet the needs of the building, but we've also done so, meaning allowing the system to operate as efficiently as it possibly can do. I think the key thing to take from this today is not to underestimate how much land you might need. You do need quite a bit. In terms of sizing the collector array, we can show you exactly how dangerous that is going forward, but really it's really important to understand the needs of the building and understand what the land can give you in terms of a heat output. In terms of the manifold point and the manifold pits, and this is something we'll come to in a bit more detail, but really the manifolds should be located at the high point of any collector array. And that's to ensure that if there are any airlocks that form within the pipework itself, which is obviously buried, and you don't want to do that anymore, you don't want to do that more than once. So once it's buried, you want it out of the way. Once the manifold is at the high point, if there are any airlocks, then what will happen is the air will naturally rise to that high point and vent from the manifold location, rather than creating a blockage or an alarm within the system itself, because the heat simply cannot get back to the plant room. And that goes for equally understanding how we design the collector array to work then into the plant room. Is there going to be a high point in the middle of the flow and return? And if there is, what are we going to do about it to ensure there's not going to be an issue long term? So in terms of the look, and I don't want to underplay how bad your field will look when this is being installed. It will look like the Somme, and it will be a shock at first, and it always is, because there's a huge amount of trenches being dug, and from trenches comes a huge amount of spoil. But the main thing to focus on is that it does go back to new. So in terms of the trenches, you need them to be at least 1 metre wide. Up to 150 meters long is ideal in terms of pressure losses and pipe runs, and between 3 and 5 meters apart. And the reason for the separation is twofold. One is that you're never then putting too much pipework in too small a space, which is vital, and we can come to that again in the future. But the second is to allow a good groundwork contractor to separate top and subsoil. So then when you do backfill, you should expect the ground condition to return to its previous state. And as you can see here, this is a barn conversion in the Cotswolds. We've come from what is an utterly shocking image of trenches open and soil and spoil everywhere and anywhere, to an image which is the green and pleasant land of the Cotswolds in the UK. And that field that you can see there, which is lovely to look out on and walk the dog within, is currently heating the building in the background. And that's how a ground source heat pump can recover, given the time and given the correct installation method. In terms of our design and our delivery, as you can see here, this is a large estate in Oxfordshire. And what we have here is essentially I will admit that the design on the right is quite rough and it's quite approximate, but it's implemented, as you can see, it's how it's been implemented and how we've designed that to work within the confines of the field. So we've avoided trees, the potential root infrastructure, any TPOs, tree protection orders that might hang over those trees. We've avoided all of that whilst also carefully ensuring that there's enough pipework there to heat a grade 1 listed country estate. So focusing on horizontal collectors, I think the things to think about and the things that any installer should be going through with you as part of the design and part of that consultation is the geology. So understanding what the ground can give you in terms of heat, gradient and undulation. So if you are living on the top of a hill or at the bottom of a valley, or you have land which rolls and rises and falls, how we can design our system to work within that sort of field. Obviously, not everyone lives has a large flat paddock. So there are certain circumstances where we might need to carefully design the system to work within the confines of the land itself. And then I think most importantly is obviously how much land do you need and how much pipework do you need? And if the two don't marry together, then we've got to look at other options, and we can come to those. In terms of trees, we want to avoid those as well. So obviously making sure that we're able to work around trees, or there's a plan in place if we need to come through trees. And then another question is, do you need sand? In some particular soil types, you may well need sand. So obviously I live in the Cotswolds. It's particularly brashy here. So the introduction of sand to the collector array may well be needed. And that's simply to protect the pipe as you backfill. What you don't want to do is go to a great length of putting all this pipework in, backfill it. As you're pressure testing, you realize as you're backfilling that there's been a leak or a hole form, and therefore then you need to replace that bit of pipework. So a bit of sand, even if it means just blinding, spot blinding as it's known, so putting sand down in certain areas where there's particularly brashy or hard sharps within the soil, just to protect the pipe, is well worth doing. Trench separation, as we've come to, that will also be important. And then pipe size in manifold location, so understanding how big the pipework needs to be to effectively collect the heat that you want. And a smaller pipe does reduce costs, but ultimately it increases the work that a pump in the plant room has to do, and it reduces the heat carrying capacity of the pipe as well. And then finally, could you slot trench? So as you can see, the image on the right is what's known as a slot trencher, or sometimes in the industry they call them a ditch witch. And essentially that is cutting a very thin trench right the way through the field, and the pipe is then being pulled in behind that trench. And the reason you might want to do that is because, as you can see, the spoil and the mess that it creates is significantly reduced, and the land has been known to return back to its former condition much quicker. Specialist contractors can do this for you quite comfortably. Not everyone has access to this sort of machinery there. So focusing on the biggest mistake, we insist entirely that all of our horizontal collector arrays are installed in the method to the left-hand side. So that trench is 1 meter wide, you're running pipework down the one side of it, you're looping at the top, and you're coming down the other side of it. That ensures that you're never going to collect too much heat from too small a space. It will cost more to install the system this way, through a combination of trenching costs and potentially through the increased amount of pipework you might need. But the long-term benefit to you in terms of running costs and efficiency and performance will far outweigh that cost, and I cannot emphasize that enough. How it shouldn't be done is this coiled slinky pipe. I would strongly advise that if you are looking at potentially someone's talking to you about installing a ground source system in this way, insist that they go down a straight pipe route. And that is simply because it will take far too much heat from far too small a space. And as you can see from the image on the right-hand side, this is the impact of putting too much pipework in too small a space. You will have permafrost, the ground temperature will reduce, the temperature of the ground reduces, so too does the efficiency of the system, because ultimately there's less and less free heat from the ground, and therefore you will expect a significantly reduced level of performance and efficiency with the heat pump, until eventually the heat pump just fails. It won't go on working in the way you want it to work in. So if land isn't available to you, one option is to drill boreholes. And boreholes are a very effective way of getting heat from the ground around you. It's probably how people might best understand how we can get heat, because on paper it looks like we're drilling into the Earth's crust. We're not quite going that deep, but we are certainly going up to 150 meters deep. And that means we're getting 300 meters of pipework per borehole. Essentially what we're doing is that we're able to extract quite large amounts of heat from the ground beneath our feet, and we require much less space. And obviously the mess it creates and the area it requires is much less. So if you're a commercial development, perhaps where you have grounds or businesses open to the public and you want to avoid mass disruption, then certainly looking at boreholes in the corner of a car park somewhere is maybe preferable. You will still need to have a minimum of 8 meters of separation between each borehole. So don't underestimate that. Again, it's not the same rules apply in terms of space, but the space requirements are a lot less. Just if you have any questions at all, please use the Q&A function, and we'll come to those later on in the presentation at the end. I hope that's okay. So with boreholes, as you can see, in terms of design, this is how we design them. Essentially, as you can see, the circles, the black circles surrounding each borehole location is essentially the agreement on space, so how much space we need, and we can fit them in a much smaller location. So what I've tried to marry up the pictures as best as I possibly can, but not quite. But what you've got there is essentially a borehole array drilled deep into the ground beneath our feet in what is a relatively small back garden or paddock or corner of a field, as you can see. There is a bit of spoil, there is a bit of mess, particularly if they're doing what's known as water or mud drilling, because they will need access to water, which will cause quite a lot of dirty water to come up out of the borehole. But again, a good drilling contractor will manage that process for you and will ensure that spoil can be removed from site, or liquid water or liquid mud could be run away from a sensitive area, for example, a formal garden. In terms of things to think about, this is a site we were on recently, so I've been sent this photo, which is very kind of our drilling contractor, but essentially the things that you need to understand when it comes to drilling boreholes is space. Again, If you need 4 boreholes, you will need to ensure they're separated by 8 to 10 meters of space. So they might not fit in a parking space at the front of the house. Again, the number of boreholes you need and the size and the depth and the volume will all be dictated by the heat loss of the building. So understanding the needs of the building is essential to the size and the design of the borehole array itself. So the first thing is access to water. As I alluded to, you can use what's known as air drilling. And I understand from speaking with our drilling contractors that air drilling they like doing in terms of when there's a bedrock or when they're drilling into granite, because they can just smash straight through it. But in most conditions, I think that our clients, our drilling contractors opt for water drilling, and they will need access to a water supply. So be prepared for them to use quite a lot of water. If you're obviously on a borehole, that's not a problem. But if you're off the mains, there might be a cost there just to think about. It won't be tens and tens of thousands, but it will be a cost just to think about in the back of your mind. In terms of the rig and the access to the site, it's obviously can be quite big, and the rig is, the bigger the rig, the quicker the job is, I would suggest. So we've got to understand that. So as part of our consultation, we're looking about how we can guide that rig to the area that we want to drill in. And I was on site recently in Devon this week, and it was a case of just understanding there was a perfect area to drill. How do we get there and working that through? And it's important to work together. So we've gone away, taken some photos, and we'll be liaising with our drilling contractors going forward. Cost considerations, it is more expensive than opening up trenches. There's no two ways around that. However, as the project increases in size, the difference in cost becomes a lot more manageable. So the bigger the project, in fact, boreholes, it may lend itself better to boreholes. Again, minimum separation, geology is vital. So understanding clearly what the ground can give us. In terms of a drilling contractor, we will obviously do a full geology report as part of our borehole design, but we'll then issue that report to our drilling contractor when we're requesting a cost, for example, and they will essentially confirm it. So by the time you've received a cost for the drilling of the boreholes, there's been 2 minds focused on the design before you've even received the figures involved in terms of installation. And then the other thing to think about is, depending on the contractor and who you use, whether or not the price is fixed. Because obviously, if we're drilling into the ground, some of it may well be a bit unknown. And as long as you've got a contractor who has caveated and covered themselves for that unknown in terms of their pricing, so they know that regardless of what they find, they've got a solution for it, then their price should really be fixed. And fixed pricing is essential, I believe, when you're undertaking a project of this scale. Open or closed loop. So I briefly alluded to that at the start of the presentation. Open loop systems involve taking heat from moving water out of the aquifer and out of the ground beneath our feet and bringing it up and passing it over a heat exchanger. And they can apply in streams and lakes, but equally when you're drilling boreholes. Open loop will reduce drilling costs because you only need perhaps an extraction and an injection borehole, but they will increase maintenance costs because you'll have to think about things like filtration, pumping costs, the maintenance of that equipment, and just the running costs of that side of the system. And my colleague Bertie a few years ago actually wrote quite an interesting article on our website about that. And I would suggest that if you're umming and ahhing about which is preferred, read that first before making a final decision. I would hang my hat on the fact that about 95% of our systems are certainly closed loop installations. And then if you are building a house remotely, you may well be drilling for water. And if you're doing that, then you've already gone to the great cost of mobilizing a drilling rig to the site. So then you might as well drill for heat as well. So if you're planning on building and drilling for water, do seriously consider drilling for heat as well, because by the time you've gone to the effort of getting a rig to site, you've gone to not half the cost, but you've gone to a huge cost of the project itself. So in terms of how we collect heat from water, this technology is known as energy blades. This is a technology which is very close to our heart, and in terms of how the technology has been developed, it's proven itself to be a really effective way of collecting heat from relatively limited flowing sources of water. That doesn't mean you should get away with putting it in a stagnant pond, because flow rate and velocity are quite important to the ability of the blades themselves. But once you understand, again, the needs of the building and you understand the availability of the water source, so is it year round? Is it going to be flowing constantly in the summer? Is it going to be moving at a fairly slow pace for most of the year? Then you can design an energy blade system to work within the confines of that water source. So these are a really effective way of collecting heat if you don't have the land and you want to avoid the cost of drilling boreholes. We don't need a huge stream. What you see here is essentially a trench which is being created to capture the water, and the blades then placed within that trench. So we have a flow in and a flow out. In terms of best practice, what we're looking at doing is the flow to come in at the top level, the high level, at the back of the blades there, you see in the top left-hand corner, and then with the outflow at the bottom and the bottom right. And therefore, we're essentially forcing the flow of water through the blades, and there we can increase the amount of heat we're able to collect per blade. So for example, if you've got, I don't know, a 300 square meter listed house, you will probably need a couple of these blades to cover all of the heating and all of the hot water elements. In terms of the look of them and the size of them, they're around 3 meters long, about 800 mil wide. And what you see here on the right is an image of a fantastic site up in Shropshire, which I think has done a brilliant job of making the blades and the position of the blades look absolutely perfect within the building itself and then within the grounds. And it's feeding into a 40 kilowatt ground source heat, a water source heat pump. And the plant room is on the left, the collector is on the right. So if you have a stream running down the bottom of your garden, or you're fortunate enough to live on the banks of a river, or even if it's just a spring flow coming down from the hillsides in Shropshire or Wales or wherever you may live, then we can capture that. And through careful design, we can ensure that you can have a year-round heating system, because when the water is flowing at its greatest is when you need the heat the most. Now, there is no reason why you couldn't combine this with another collector. So for example, there's a couple of sites we've worked on where they don't have a year-round water source and they don't have enough land for an exclusive ground source heat pump, i.e. they don't have enough land to put all the pipework in the ground that they need for the building. And therefore, careful design allows us to balance the two technologies so that the water source is obviously complementing the ground source in the very depths of winter, because the flow of water through the blades at that point is far, far higher than the summer when there's very little flow, and the energy needs of the building, which at that point are very, very low, are serviced by a reduced collector size in the field. So in terms of the heat transfer, this is quite important. If you just put them in a stagnant pond, you're going to get about 8 kilowatts from them. And if you put them in a fast flowing stream, you'll get about 20 kilowatts from them. Fast flowing streams often provide more energy than maybe slightly slower moving large volumes of water. And it's all down to the flow rate and the velocity. So as you can see here in this image, what we've done is we've installed them under a pontoon, and we've actually had to install a number of blades because we're accounting for the slightly reduced flow of what is quite a slow moving body of water. So what we're looking at here is flow rate and volume of water, the number of blades required, because again, once you understand the needs of the building, you can then design the collector, how to collect the heat around that. The installation method, so are we going to be able to get to the blades if we need them? So can we service them? Could you put a garden brush through the blades if you needed to get any leaves or give them an annual clean? And then obviously the route back to the plant room, again, taking into account the undulation of the land. The water is usually at the low point, but who knows? Is there going to be a hill or trees we have to avoid? And then another key question which always comes up is debris. You often see, perhaps after a storm or in particularly wet seasons, a large log floating down the river or the stream. And what do we do about that? So one option is just to simply create in our yard, in our office, a steel plate, which allows you to deflect debris away from the blade. So what we don't want to do is prevent flow through the blade, but equally we want to just move debris along, shall we say. We want to keep that traveling down the river to make it someone else's business. And then, as you can see, the next thing is boats. So are we going to be in the way of boats? And that is actually quite an important question, because what you don't want is a barge careering through your energy blade, your nice energy blade installation, just as it's installed. So what we've done here is we've protected it with the pontoon, and that equally allows us to service the system very easily. So the next way of collecting heat is through lake loops. And whenever myself or my colleagues go to a site and we see a nice large lake, we always get very excited, because a lake gives us huge amounts of energy from a relatively small body of water. So it doesn't have to be huge, but the joy of lakes and water and ponds is that they often have a flow in and a flow out, and they're able to replenish their energy at a much quicker rate than the ground. So therefore, we can go down the route then of using a slinky coil, because the energy replenishment rate is far, far quicker than that of the ground. So we're able then to coil up the pipework, we'll sink it to the bed of the lake, and it will slowly in time be submerged by silt, no doubt. But equally, regardless of that, even if the lake is fairly silt-free, just the sheer depth of the lake usually means that any pipework is quickly hidden and out of sight. So the site you see here is a listed hotel in Cheshire. Again, actually, in this site, we've combined a lake source system with a ground source system, because the lake wasn't quite big enough and the ground wasn't quite big enough, but to combine together, they work very well, effectively together. And the other main benefit to a lake source system is obviously you avoid the need to open up significant amounts of trenching. Now, we will need to have a trench coming back to the plant room from the lake, but you're not opening up all these trenches that you see in the field. So there's a cost which you save there. And so what you're then looking at from an installation point of view is you're having a reduced amount of pipework, because you don't need quite so much pipe, because the replenishment of the lake is, and the energy in the lake is far, far quicker. And you're avoiding a trenching cost. So therefore, the economies of scale in terms of value of investment becomes very, very attractive. In terms of lakes, they can be adapted to heat large country estates, as you see here. And what I wanted to do is show you this design, because you can see how we've carefully worked out how we're going to structure the collector array within the lake, whilst also ensuring the manifolds, these red dots, these 3 red dots on the southern side, are able to be easily accessible and serviceable for our engineers going forward. In terms of the lake loop, as you can see, some of these are coiled, some of these are slinky. And what we will do is our engineers will be in a boat and waders if the depth allows us to, and we'll be able to work these collectors and slinkies into the area that we want them to collect heat from. Again, the same principle applies. We don't want to put too much pipework in too small a space. Now, you may well you may ask, what happens if my lake freezes? Well, often a lake would freeze on the top, but actually down below, deep within the where the fish still live, a metre or so down, the water temperature may well be held at a more constant 4 to 6 to 7 degrees, and that is the place at which we want our pipes to sit. So even if there's 6 inches of snow on the ground and a layer of frost and a frozen lake, the collector array and the heat pump can still perform in the very depths of winter. But again, we don't just do large estates. We also do smaller properties, new build properties. So here we have a building which is being created where there is a lake which is being built around the property itself, and the collector array is going to be sat within that lake, servicing a plant room which is immediately the other side of the lake wall. And there we have quite a small pond, you would argue. I know we've referred to it as a lake, but it's about 25 meters by 25 meters, so it's not huge, but it's servicing a new build house which is going to have all of its energy needs, heating and hot water, provided exclusively by the water it is overlooking. And then from a carbon point of view, the savings are exceptional. Running costs are far, far lower. There's an incentive scheme that's available to this client as well. And if I dare say, it's pretty cool. So in terms of a lake source system, the things we're thinking about, again, width, length, and depth. So understanding how big is my lake, how much water is in there in terms of volume, what sort of depth is it? Is there a flow in and is there a flow out? Now, it's not the end of the world if there isn't, but if there is, and that's brilliant, because obviously flow in brings more energy and flow out takes away cooler energy. So flow in and flow out is obviously quite useful from a sizing perspective, but not essential. Shading also has to be considered, because a lot of the heat that we extract from water comes from the sun and obviously rainfall. But shading then obviously can have a bit of an effect on that. So it's really important to understand when you're designing your lake system, have you accounted for shade? And I would suggest that at isoenergy, what we like to do is assume there is no flow in and there is no flow out, assume the minimal depth based upon what we've looked at site or what we've been told by the client, and we assume a maximum amount of shading. That way, we know that the design of our system has assumed the absolute worst case when it comes to how we're going to put this into the ground and how it's going to work effectively. And then from there, we know that regardless of what might happen on the site going forward, if someone comes along and plants 200 trees next to the lake, or whether or not someone, the local farmer, blocks up the flow in, at least then we've got a system which is designed to cover the needs of the building in the worst case scenario. And then the other question is, does it need dredging? So you may well have purchased a property with a pond or a lake, or thinking about dredging your lake. If you're doing that, then here's the perfect time to put in a collector array. If it does need dredging, bring that decision forward, do it as part of the collector array, get it in, get it done, and you're again increasing the volume of water held within that lake. One of the questions that does come up occasionally is bathers. So obviously, as you can see, the pipework is coiled. It will be submerged to the lake, and the image is shown as the installation is ongoing. But what we don't want to do necessarily is put any bathers at risk. So we just need to understand that, and we need to talk to our clients about that, work our design around their needs, but whilst also trying to submerge the pipework perhaps within the silt itself rather than just laying it on top. So therefore, it will be covered and out of the way, so bathers can go about their business without the risk of getting caught up in the collector array, obviously. And then again, as we've looked at with all of these things, the route back to the plant room. How do we get there? Do we have to navigate it? Trees? Do we have to come through walls or under walls? Do we go up or down? Whatever it is, all of that needs to be carefully considered, understanding potential high points, highlighting that to a client. What can you expect as the client to see at the end of the process? And will I need to think about anything in particular in terms of enabling works or other services to get in and get out of the way? So the final thing I wanted to focus on was all to do with manifolds. So manifolds are a really important part of a collector design. So regardless of whether we're using collecting heat from a horizontal system, from boreholes, from a lake, or even from a number of energy blades, the use and implementation of a manifold and the design of a manifold is essential to the success of the collector array. So again, it's all very well having all the pipework in the ground, but if you can't service it easily, or if you can't identify an issue if there ever is one, and I would suggest you shouldn't really expect there ever to be one if it's being held under pressure whilst you're backfilling and everyone's signed off the pressure certificate at the end of the installation process. But if there is ever an issue, how do you identify which loop or which circuit is the issue, is where the issue is? The manifold location is critical to that. And being able to work within that manifold, being able to access all of the connection points is quite important. So there are a number of different manifolds that you can use. Some more popular options are these sort of circular manifolds that you sometimes see, where there appears to be lots of different connections going in lots of different ways. We definitely don't use those for a number of reasons. One, because of where the connection points are. Sometimes they're difficult to get to, difficult to access, difficult to service. Would you need to bring back a ground worker to excavate the manifold if there was ever an issue, for example? You don't want to do that. So what we do is we create a manifold chamber and a manifold pit, and that way we can access the flow and return from one side, as you can see on the left-hand side of the image on the right, and the collector array on the right-hand side, all going out underneath the manifold chamber itself. So there, what we have then is essentially all of the connections are within the manifold chamber. So any potential weak point is not only accessible, but it's fixable without having to excavate huge amounts of pipework and ground. What you also have there is the ability to essentially top up all the glycol nice and easily. To hide the manifold, as you can see, a silver lid is simply all you'll see. And if you really wanted to, you could cover it with a bit of turf or a plant pot or a bench or something like that. And then also, as I mentioned earlier, the high point, making sure you put the manifold at that high point, because if there is a risk of airlocks and there's glycol within the pipework, so there's potentially bubbles within that which might form to create a larger bubble, we want to make sure that works its way up to the manifold high point, so there it can be vented, And then equally, the next ventilation point will be within the plant room. So therefore, in terms of design, the collector array design, and more importantly, the manifold design, is essential to the future proofing of the system and to ensure the longevity and the long-term success of the installation. In terms of manifold location, if you are thinking about, I don't know, drilling boreholes in the parking area outside your house, for example, then you could consider a factor B manifold, and that's a concrete plinth beneath the manifold itself, and a particular lid to allow vehicles to pass over the manifold without any disruption, without it giving way or breaking in any way. So again, part of that consultancy and part of that design with isoenergy is to understand what will come over these. You know, we might be stood in the corner of a field somewhere in the middle of nowhere, but if the farmer has to access that corner of the field, or if you know, you have a large sit-on mower, will the manifold lid be able to cope with that? And if not, what can we do to prevent any accidents from happening? So to summarize, what we want to do is really, in terms of the design, it is the most important part of the heat pump system in the design of the overall system. So it's all very well having a snazzy looking plant room, but if the design of the collector array is not done correctly, you will suffer long term, and the cost of either making good of the mistake you've made or having to live with a system which is costing you a lot to run will be far, far greater than the cost of doing it right in the first place. So emphasis, it should always be on how much pipework you're putting into the ground or the lake. Is that enough for the needs of the building? What's the evidence to support that? And I would suggest a good installer should be able to provide that evidence, and if not, why not? And then in terms of how it's laid out, understanding the dynamics of the installation, is that going to work within the confines of the space that's available? Is that going to work long term? And if the answer to those questions, any of those questions are no, or there's a doubt over those, think again. So don't squeeze too much pipework in too small a space. Don't install slinky coiled pipework in the ground because it will take too much heat from the area it's within. Don't undersize the amount of drilling you're doing just to save costs up front. And if there is a lake, understand the needs of the lake and understand the requirements of the building within that lake, and understand exactly what the lake's going to give you. So put huge amounts of emphasis in terms of the design on the collector array and how we're collecting heat. And if you are using a contractor or an installer who has the answers to all those questions, you should feel absolutely certain that the heat pump is going to do exactly what they say it's going to do. It's going to perform exactly as they say it's going to perform for the longevity of its lifetime, which is 20, 25 years for the plant room equipment and 50 plus years for the pipework in the ground. And more importantly, the carbon, the savings and the performance of the system is going to live up to expectation. And that, from our point of view, is we hold above everything else. So we're happy to deliver our systems to a very high standard, knowing that the performance of those systems will be exceptional in the long term. So I hope that's been useful. Perhaps now we could move on to any questions that we have, and I will just work through those questions now, so bear with me. In terms of, so if you don't mind, I will start at, so if I look at the chat feature, I'm answering a question from MJ London. It says, to reduce heat losses, ventilation might be reduced. Any problems with condensation? So I presume you're talking about how we design a system within the building itself. So if you're working in a particular, for example, a really airtight property, which has been built to very high standard, then and ventilation is therefore reduced, then often mechanical consultants, or even through our own expertise and instruction, we might recommend an MVHR system to counter that issue. In terms of the ventilation, I agree, it's equally as important, and it's something to understand. So Chris Kemp and MJ Lunt, you're referring to ventilation and condensation. I would be in full agreement with you that ventilation is an important part of any building design and should not be underestimated. So Elliot Sim has kindly answered the question for me as well. Harriet, do you need planning permission for the trenching? This does depend. It's a slightly complicated question because obviously every council is different and the needs of every building is different. I would suggest that for the vast majority of properties which are not listed, it will be seen as permitted development and you should pursue on that basis. It would always be worth double checking with a planning officer and getting written clarification of that for obvious reasons. If it's a listed building, I would start with the assumption that you do need some form of planning and to open up the dialogue with your council and your planning officer. isoenergy designer provide full designs for the system. So some of these you've seen examples of in this presentation, and those designs can be used as part of a wider planning application. So if it is something you're looking at doing seriously and you want to pursue this, then designing the collector array might well be worth doing before you go in for planning. And it's a small cost to do so, and that would ensure then that you have all of the information to your planning officer. What you could also then do is ask the consultant from isoenergy to assist with any questions that they may come back with, because planning officers, as good as they are in places, do have lots of very unusual questions which do need careful guidance. And we have the answers to all those questions, and we can make sure they're answered satisfactorily. Presumably with a slot trench, you need one for outflow from manifold and another to return it to manifold. Yes, you do, and often I would suggest that slot trenching tends to be implemented when you have a nice big flat field where you can just simply open up lots of slot trenches for the collector array. You will still need to have some excavation, so it doesn't get rid of the excavation issue entirely. You would have to excavate perhaps down at the end of each slot trench to allow the pipe to loop within that court at the end of the trench itself, and you would need to excavate for the manifold pit as well. And then because you're excavating, it might actually be worth excavating for the flow and return, because the pipe size, depending on the size of the property, may well be quite chunky. For example, 200 mil, 160 mil MDP plastic pipe, the machine, depending on the groundworks contractor, may not be able to cope with a pipe that size. So slot trenching is great in places, but certainly you would still need to have some minor bits of excavation, and the flow and return back from manifold to plant room may well be one of those items. And then Paul Clark has kindly asked, what is the minimum distance between boreholes? That you might have missed that, Paul. That's a minimum distance is 8 meters. So making sure that there's enough separation there. Will this webinar be able to view online? Yes. In terms of minimum depth of lakes, we would recommend a minimum depth of 1 meter, but we can work with less. And the reason we can work with less is because we have to carefully understand the volume. So the depth obviously plays a key part of that. So if the lake is shallower than 1 meter, then as long as we understand just how shallow it is, we can carefully design the lake collectors to suit. So if we have any concerns about the volume, we will highlight this as part of that design, as part of that consultancy, and we will come back to you with other options. So for example, you can get X amount of pipework in the lake, but the volume doesn't support anymore. Therefore, we're going to open up a couple of trenches alongside the lake to fit some ground loops within. Do you ever fit an extra loop for redundancy? Yes, in short, we do. And I would suggest that the design that we go to in terms of isoenergy, we're rounding down the thermal conductivity of the ground and rounding up the requirements of the building at all times. So by default, our design should cover any should cover any additional heat loads that may be applied to it later on down the line. It's really important just to assume worst case when it comes to designing a collector array. And are there planning considerations for ground loops, boreholes, or water source? Yes. If it's rivers, then we have paperwork from the Environment Agency confirming that they're happy with energy blades in particular, because it's a closed loop system which doesn't extract anything from the source. So we're not drawing water from the source. It's all very closed and non-toxic. If we want to get particular permission from the Environment Agency from your site in particular, then we can do that, although it will drag the process out, and I suggest the answer will still be the same. Yes, it's fine. In terms of experience of installing in a church with a graveyard, a vertical borehole better. We've installed in a lot of churches, and yes, almost all of them, I believe, are boreholes. And what is the approximate number of boreholes for an average four-bedroom house, typical new construction brick and block in the UK? I would suggest, Paul, that you're probably looking at a couple of boreholes, 100 to 120 meters deep at most, depending on the final floor area. And then if I just go on to the Q&A form. So with ground arrays and pipework, how does this get recognised by local authorities to avoid future damages? So in terms of with ground arrays and pipework, how does this get recognised by local authorities to avoid future damage? In terms of installation methods, it's often useful to put sort of tracker tape above the pipework. You could also put some form of protection above it to a point, but really it's going to be a meter deep, and as long as you have sufficient tracker tape there and a sufficient services drawing, I might add, then that is usually enough to avoid any potential damage going forward. In terms of local authorities, I would take that on a case-by-case basis, but if there's a particular issue that a local authority has or wants us to overcome, it's nothing we haven't done before. Is the manifold shown for water source slinkies, or will it take 40 mil ground pipe? So is the manifold shown for water source slinkies, or will it take 40 mil ground pipe? I'm just thinking about that question, Martin, but the manifold is shown on the edge of a bank for water source systems. So if you were putting pipework in a lake, it will all come back to that manifold on the bank side. Again, nothing which a nice park bench couldn't sit on top of if you wanted it to. And that manifold will then be the access point to everything in the lake. In terms of the depth of that manifold pit, it's usually about 1.2 meters deep, and that's again just to allow ground level to come flush up to it, up to the lid. And Amar says, I've heard of a two-stage heat pump which provides higher flow temperature. Do you have more information about this? Well, to answer the question, Mike, yes, there are high temperature heat pumps, and in the right settings, they're useful. So, for example, we're installing a system at the moment in a pub, which has a very high hot water demand. Therefore, a high temperature heat pump is going to be the most useful part of that installation, because it will allow us to hold 2,000 litres of hot water in this case at a very high temperature, which is obviously going to be used for kitchens and infrequently at peak periods in the hotel, in the rooms. I would suggest, though, that with sufficient design, you shouldn't need a high temperature heat pump. So the reason people talk about high temperature heat pumps, and perhaps people like the idea of a high temperature heat pump, is because they seem to replicate the performance on the flow temperatures of a conventional boiler. If the system is designed correctly, though, in terms of how it distributes heat and how it trickles heat into a building constantly rather than trying to replicate the actions of a boiler, then you should be able to avoid the need for a high temperature heat pump, because they do run slightly less efficiently and they cost quite a bit more to install. So my answer to that question is yes, they are available, and in the right settings they should be applied. But equally, the first point of the first thing to look at should be a low temperature system to ensure that you're covering all the boxes there and you're ticking all the boxes. And if that is practically just not possible for whatever reason, then we look at the high temperature versions. So Jonathan says, you haven't mentioned efficiency of ground versus water versus air. Briefly, water is the most efficient, and so a benefit of going with this method is, if possible, is that correct? Yes, Jonathan. If I was to put on a sliding scale the level of efficiencies that you should expect to get from a heat pump and what is the preferred option, I would always start with water. And as mentioned, we get very excited when we see water. Then it's ground, and then it's air, essentially. And there's a minor difference in performance of ground source systems between boreholes and collector. Not huge, and not necessarily enough to justify the difference in installation cost, but there is a small difference in efficiency. Water is the most efficient way of collecting heat, and as an organisation, we love working with water because of the efficiencies we can be certain of getting through our system. We know we can deliver a really good system off the back of that. But regardless, ground, water or air, all of them will provide a significant carbon reduction versus fossil fuels and a significant running cost reduction versus fossil fuels. And that should not be underestimated. There are preferences, obviously, and we will look to get the best out of the surroundings of a building, but certainly all of them should be considered for any building going forward that you might be considering or buying or working on or whatever it may be. So as far as I'm aware, I think I've answered everyone's questions. If there are any more, you can see our contact details there. In terms of the presentation, I'd like to just thank you. Oh, there is one more question I can see, sorry. I would like to thank you for the presentation. Sorry, Paul's just asked a final question. What is the limiting efficiency of a heat pump if used for both heating and cooling the property? Is there a better mix between the ground systems that you've discussed? There's no limiting efficiency as such, Paul, but we have to understand the heating and cooling needs of the building. Certainly, cooling often lends itself very well to boreholes because you can, the way you can design a system. But again, the cooling needs of a building need to be carefully understood. So the type of cooling you might need, and again, tie that in with the type of heat pump and how we control that. So certainly, in terms of the efficiency of a system, it shouldn't be compromised just because cooling is also being considered if it's designed correctly. And I'd be happy to go into that in more detail in terms of the individual project you might have, because at that point we can apply it to the specific heating and cooling needs you might have. So I hope that answers everyone's questions. If there are any other questions, you find all of our contact details there. It's been brilliant, a fantastic presentation to be involved with, and I really appreciate you taking the time out of your day to listen to it. If there are any questions, do get in touch.